So next up, we have Yang Gao, who is going to talk a bit about a phase study on lunar volatile and mineralogy mapping orbiter mission. Yang, if you're there.
Yeah, I'm here. Can you see my screen?
Yep, we can see your screen, and whenever you're ready, I will start the timer.
Thank you, John. Hello, everyone. It's a pleasure to be here speaking on behalf of the VMMO consortium, consisting of members from the UK, Canada, Portugal, and the Phase A study for the mission is managed by European Space Agency, the CubeSat office at Aztec in Netherlands. Just some quick words about the history of the mission. The concept has started since early 2017 in response to ESA ITT on 6 Nova Challenge on Lunar CubeSat for Exploration program. And we've been very fortunate to be selected as one of the joint winners for the challenge. And that gave us the opportunity to use ESA's CDF facility to further the study in mid-2018. At the beginning of 2020, the formal Phase A study sponsored by ESA was kicked off with a consortium that you are seeing today. And we have successfully completed the Phase A in March 2021. In this Phase A study, there are a number of flight opportunities we have assumed for orbital release of the CubeSat that include 2 NASA programs, the Whipper and Artemis 2. Just to highlight objectives of the mission, there are 2 folds. Technologically, we are looking at demonstrating beyond LEO 12U CubeSat, its feasibility in terms of using some of the core electronics as a test bed and semi-autonomous operation, particularly in terms of navigation and ranging, considering another potential onboarding SS receiver. There's also a tech demonstrator on optical high-speed direct-to-earth downlink. This is likely to reach up to 100 megabps. Scientifically, we are looking at mapping principally volatile mineralogy using multi-wavelength LiDAR. There are multiple channels for the payload and looking at abundance mapping for water ice and ammonite in this case. In terms of the target area, we are looking at South Pole Shackleton crater as a priority for the mapping for the science payload, and it's not very difficult through the STK simulation to establish how long the mission has to be in order to map a crater as a size of 20 kilometers across the diameter. So giving those information in hand, and we also had various mission constraints provided by European Space Agency during the Phase A. Everything had to be accommodated within a 12U CubeSat with a wet mass up to 24 kilo with margin. In terms of the CubeSat deployer, we are looking at ISIS COPPAD 12U XL. And as mentioned earlier, there are 2 NASA missions that have been baselined to potentially inject the CubeSat into a transfer orbit. Launch time frame, we're looking at Q4 2023 or up to 2024. 1 year mission duration as a baseline in order for us to cover very well the entire Shackleton crater. So this is a slide give you a kind of overview of mission profile, very much echo what I said earlier, from the integration with the mother spacecraft, depending on which flight opportunity we have in mind up to launch and transit to the moon. Of course, the spacecraft release that includes a detumbling, solar array deployment, and of course the orbit acquisition, which here we're assuming a lunar frozen orbit as the final orbit, and that lead to the start of the 12 months operation for the mission. I think it's worth highlighting some of the operational concept for the mission, particularly some of the communication routes, if you like. There are 3 communication routes back to Earth. There's UHF link via the SSTL Lunar Pathfinder orbiter. That's going to go through the Goonhilly ground station based in the UK. There is S-band, X-band, depending on whether we have the GNSS on board for ranging. Direct to Earth link, which rely on either UK-based or ESOC-based station network. Also, last but not least, the communication to support the optical data link, which has to be using an ESA station, which is equipped to support that. The spacecraft operation is going to be based at Surrey in the UK, and the payload operation is going to be managed by MPBC, our partner in Canada. Of course, the rest of the consortium is split into these 2 teams to support the platform operation and the payload. The science team is obviously going to be in charge of the processing, distribution, and archive of the scientific data and how to interface some of the data outputs with support from the international science community. A few words about the science payload requirements for Phase A. There are 3 channels for the LiDAR to support active mode, where we want to achieve the signal to noise ratio of about 30. Ground sample distance within 10 meters. For the passive mode, we're looking at 4 channels to support mapping both the water ice and ammonite. So for the payload, it needs to be kept within the 5U of the platform and has to be less than 7 kilo, and the peak power has to be kept at 140 watts. This is just an overview of the configuration of the CubeSat from the outside. From the inside, there's a bit more information here about the data bus and the power bus. As you can see, we baselined the CAN bus principally, supported by space wire. And there's something we're also using RS422 to support the control of the electrical propulsion. This is a summary slide to just confirm that the Phase A managed to keep everything within the mass budget we're being asked to do by ESA. So all the subsystem has been kept within 24 kilo with a reasonable system level margin of 15%. The breakdown of different subsystems in terms of percentages, quite reasonable. I would say if you look at the statistics, this is not far off from what typically happen in satellites in average. I just quickly ask John, do I have 4 more minutes?
It'll be 2 minutes once the clock reaches 4 o'clock.
I didn't realize I can go so fast, so I can go quickly to some of my spare slides, utilizing that 2 more minutes. So just a few backup slides to say a few more words about the payload itself. As you can see, it's broken into two operational modes. For the passive, it's looking at the reflectance ratio between the four channels we have there, 532, 1064, 1535 to 1560 nanometer, and there's also ultraviolet channel at 290, which provide additional safety guard for the data acquisition. Well, for the active mode, where we have less channels to look at in this case, 3 channels, and in terms of the data acquisition during passes, which are looking at both day and night, we will be looking at over at least one or more Apollo landing site. This is really to facilitate calibration, both offline and online. Just to present a few additional graphs here in terms of the actual working principle of the payload. And here we are looking at absolute reflectance and reflectance ratio. Of course, in terms of ratio, that gives us less ambiguous results in terms of mapping the water ice abundance. So here is a similar slides, but in this case, looking at the mineralogy, detection, mapping. As you can see, there's some data graph acquired from the lab work, which shows the principle does work because it gives quite distinctive gradients here in terms of the graph. And there's also the wavelength plot looking at the almanite detection through its reflectance and how that is compared looking at the existing data points based on the highland soil and marl soil. I think I might hit my time budget, so I better shut up, but I can leave this slides here as ending slides, which kind of show you a comparison of the coverage of the Shackleton crater based against the different orbits we have analyzed during the phase A study. There is also extra information about how it looks like compared to Fustini, just in case we have interest there too. Hope that's okay.
Brilliant, thank you very much.